Welcome back to the second video for dimensional analysis, or DA. Here at Bridge, we believe studying for the RD exam should feel simple and stress-free, and that's exactly what this section is for. We're going to work through a set of practice problems together, one at a time, at your pace. If any of the problems feel tricky right now, don't worry. You are not expected to master it all on the first pass. We'll keep practicing dimensional analysis throughout this entire module, and you'll see it pop up again and again throughout the course. In this video, we'll go over scoop sizes and can sizes, and then we'll get into some practice problems. These are all Domain 4 topics that'll pop up again in Module 6 on food science, as well as Module 9 on administrative nutrition management. So let's start with scoop sizes. Scoop sizes are a notorious concept on the RD exam because you could be asked a question that relies on knowing how many ounces each different kitchen scoop holds. But I've got a trick for you. Did you know each industrial scoop number tells you how many scoops it takes to make 1 quart? And a quart contains 32 ounces. That's another equivalent statement. 1 quart equals 32 ounces. So if you divide 32 by the scoop number, you'll know how many ounces are in 1 scoop. Other RD prep courses expect you to memorize this without any context, but at Bridge, we know you'll remember the information better if you are given the context. So if you know the scoop number, just do 32 divided by that scoop number. That's going to give you the volume per scoop in ounces. So for example, the number 8 scoop, to find the number of ounces in that scoop, we divide 32 by the scoop number. 32 divided by 8 equals 4. So there's 4 ounces per scoop. And the number 16, well, if you take 32 and you divide it by 16, you'll get 2 ounces per scoop. And then the 30 scoop has about 1 ounce per scoop, because if you take 32 ounces and you divide it by 30, you'll come out with approximately 1 ounce per scoop. The number of ounces per scoop is just another example of an equivalent statement, and you can use these equivalent statements in dimensional analysis problems. So as we go forward, and for all of the example problems in all of the videos at Bridge, I highly recommend you pause the video, you try the practice problem on your own, you think through it, you get stuck, and then you hit play. I'll be here to support you the whole way. And if you have any questions on anything, just drop them in the comment section below. Let's say we have a school cafeteria that's serving chicken pasta primavera, and they use the number 8 scoop. Each student is getting 2 scoops of this entree using the number 8 scoop. The cafeteria is expecting 475 students, so the problem asks us to determine how much of the entree is needed to be prepared in pounds. Since we're converting units in this problem from scoops into pounds, we need dimensional analysis. We're told that workers are using the number 8 scoop, and the equivalent statement for the number 8 scoop is 4 ounces is equal to 1 scoop. Remember, you take 32 and you divide it by the number of that scoop. 32 divided by 8 is 4 ounces. So in every 1 scoop using the number 8 scooper, that has 4 ounces. But the problem also asks for the amount of the entree in pounds, and you should know that 1 pound is equal to 16 ounces. These are both equivalent statements, and so if you want, you can write them out as 2 fractions each. Since they equal each other, it doesn't matter which value is in the top of the fraction, the numerator, and which is in the bottom of the fraction, or the denominator. 1 scoop using the number 8 scoop is 4 ounces. So 1 scoop is equal to 4 ounces, or you could write 4 ounces over 1 scoop. They mean the same thing. But since each student is receiving 2 scoops using that number 8 scoop, that is our given. 2 scoops of the number 8 scoop. And to cancel out the units of the number 8 scoop, then that is what's going to go in the denominator. The units that you're converting from will always be the same. And we can convert from scoops into ounces using this equivalent statement that we've already worked through. 1 scoop has 4 ounces. To make the units match, we need ounces on the top and scoops on the bottom. which tells us that each student is getting 8 ounces of this chicken pasta primavera entree because they're getting 2 of the number 8 scoops. But the question specifically asks for pounds of entree, and we know that in 16 ounces, we will get out 1 pound. Since we're converting away from ounces into pounds, we want ounces in the denominator and pounds in the numerator. 1 pound over 16 ounces. Meaning, if every student is receiving 8 ounces of this entree, then every student is receiving half a pound of the entree. But keep in mind the cafeteria is expecting to serve 475 students, not just one student. We need half a pound of this entree per one student, but we've got 475 students coming every single day. To cancel student out of the denominator, we'll need to put it into the numerator. This will allow us to cancel out this unit and figure out total amount of entree that we need to prepare. Since every student needs half a pound, and we've got 475 students coming, then we need about 237.5 pounds of this chicken pasta primavera dish to be prepared. Next, let's look at can sizes. Canned fruits and vegetables are staples in food service as well as in clinical settings, so it's important to memorize the most important can sizes and their volumes for the RD exam. In the real world, you'd be able to reference this, but for the RD exam, you need to know the values. So here's the general rule. The larger the can number, the higher that number is. The 10 can, for instance, has the largest volume. The higher the can number, the larger the volume. But there are a few exceptions, so let's break it down by what you actually need to memorize. Starting with the number 10 can. This is the big one. It's the one you see in industrial kitchens and in industrial cafeterias and hospitals. It's those ginormous cans. The number 10 can holds about 13 cups. The next can size I would recommend you know for the RD exam is the 2.5 can. The 2.5 can you'll find in your kitchen. It's that larger can that your home kitchen is likely to have. The 2.5 can holds about 3.5 cups of food. I personally use the 2.5 can when I'm buying the large can of beans or the large can of tomatoes, right? You can buy the small can of tomatoes, but in my household, we want the large can sometimes. So the 2.5 can is something that you find in a home kitchen. It's that larger can. And the last can number I'd recommend you know for the RD exam is the number 300, or sometimes written as the number 303 can. These are your standard home kitchen cans. It's like when you go to the grocery store and you buy a can of beans or a can of asparagus. It like tends to come in this small petite can. A can of soup comes in this size can as well. There are slight differences between the 300 versus the 303 can, but generally speaking, they hold the least amount of volume of food inside them. So typically, the larger the can number, the larger the volume. The number 10 can holds about 13 cups. As you decrease can size, your volume also decreases. The 2.5 can, that's your large home kitchen can, holds about 3.5 cups. The exception to this rule is the number 300 or 303 can. Those are your standard home kitchen cans, and they hold about 1.75 to 2 cups worth of canned goods. And now all of these are equivalent statements, which means we can use them in dimensional analysis. So let's try some. In this problem, we have a recipe that calls for 4 cans of beans using the number 10 cans. But if a facility only has the 2.5 can, then how many of these 2.5 cans will they need? Remember to try to pause this video and try it on your own. This is a dimensional analysis problem because we're trying to convert from the number 10 can into the number 2.5 can. You'll only be able to solve this problem on the RD exam if you memorize the number of cups inside each one of these cans. So the number 10 can hold about 13 cups, and the number 2.5 can hold about 3.5 cups. These are equivalent statements, which means you can write them out as 2 fractions. In every number 10 can, you can get out 13 cups. And if you have a can providing 13 cups, well, that's a number 10 can. So in this problem, we're told the recipe requires 4 number 10 cans. Now we know that there's 13 cups in a number 10 can. We want to put the number 10 can in the denominator so that it cancels out with the number 10 can that we are converting away from. We're converting from the number 10 can into cups, and we know that there's 13 cups in every number 10 can. Meaning if the recipe needs 4 of these cans, then it's providing 52 cups of beans. And we know that the facility only has the 2.5 can. A 2.5 can provides 3.5 cups. So you could write the dimensional analysis fraction out as a number 2.5 can over 3.5 cups, or 3.5 cups comes from the number 2.5 can. So in this next bit of our dimensional analysis, we'll convert from cups into the 2.5 can. Now we're trying to get cups to cancel out. So we'll put it in the denominator because those are the units we are converting from. The units we're converting to are the 2.5 can. And we know that in every 2.5 can, there's going to be 3.5 cups. So we can pick up this equivalent statement right here and plug it into our dimensional analysis. If the recipe needs 52 cups of beans and we only have 2.5-inch cans that each provide 3.5 cups, then we'll need 14.8, or more likely 15 of these number 2.5 cans. So this is just some practice that we can do with dimensional analysis, but it is all over the RD exam. So keep trying, and I will see you in the next one.